This video is a continuation of growth and decay. In the last video, we talked about exponential growth, so now we're going to focus on exponential decay. And the good thing here is that they're actually very, very similar. There's one tiny difference in the formula, and it is just a minus sign. So for exponential growth, we used y equals a times 1 plus r to the t power. Now for exponential decay, it's 1 minus r. So exponential growth is when we start off with an amount and over time it gets bigger, right? Like a population increases or the amount of money you have in a bank increases with interest, whatever. For exponential decay, it's doing the opposite and it's getting smaller. It's going down. So that's why we subtract our rate of change here instead of add it, because as time goes by, we're getting smaller and smaller according to that rate, okay? Just as a quick review also, let me zoom in a little bit here. Each of these variables in the formula are represented, or they represent something specific. So y is the new amount that we're searching for, right? A is the initial amount that we start with. R is the rate of change, and it's going to be given to you usually in a percentage, and sometimes the percentage is a decimal percentage, but if it's got that percentage sign behind it, you have to change it to just a decimal. So to change any percentage to a decimal, you divide by 100, right? So percent divided by 100. So if it was 12%, you do 12 divided by 100, which would be 0.12. And then lastly, we have t. And t is up here in our exponent. That's what makes this exponential decay. And it is the amount of time that has passed. And it's usually in years. If it's not in years, it will specify if it's in something different, like months or whatever. But usually it's in years. So yeah, let's get started. Let me zoom out. All right, first couple examples here. I always like to go through the ones they've done for you because you can just check out what they're doing and then make sure you get the right answer. All right, depreciation. Appreciation is when something is growing, right? Depreciation is when something's doing the opposite. It's getting smaller. It's depreciating, losing value. The original price of a tractor was $45,000. So this is A. This is our initial amount, our starting amount. The value of the tractor decreases. That's how we know it's exponential decay or depreciation. It decreases. Sorry, I didn't realize you can see that. At a steady rate of 12% per year. So this is R, and that's all we have. We don't know T yet. Write an equation to represent the value of the tractor since it was purchased. Okay? So it tells us the rate. We have the rate and the initial amount, and that's all we know other than it's decreasing. So we're going to write, well, I guess I just follow it along here. Y equals A times 1 minus R to the T power. A is our initial amount. The tractor initially is $45,000. And then it decreases at a rate of 12% per year, and they changed 12% to a decimal. Okay, and that's all we know. It doesn't give us any time reference. We don't know anything to put in for T. Since we can't put anything in for T, we can't solve for Y. So from this step, all they did was simplify what's inside parentheses. 1 minus 0.12, and we get 0.88. Okay, so that's the only difference between growth and decay is this little minus sign. In decay, when it's going down or depreciating, it's a minus sign. When it's increasing, it's a plus sign. All right, B, what is the value of the tractor in 5 years? So now we know what T is, right? Here's our formula up here. After we've simplified it, now I can put a 5 in for T. So that's what they've done here. Once in our calculator, I know they wrote the answer out for you here, but once we get to this step, once you've simplified down to this step, then you can just plug everything in your calculator, which is awesome, right? So 0.88, our base, raised to the 5th power. Remember in your calculator to raise, you can see the sun coming through on this grate that I use for my phone to sit on. Once we, when we want to raise something to a power, we hit this little button. Y is your base. This is our base. So you type the base in first, then you hit the button, then you hit your exponent, and then equals. So we get this amount. So all of this is that decimal amount, and then we have to multiply it by 45,000. So times 45, 1, 2, 3, and we get 23747.94. And it's in money, so we can round to the nearest hundredth. Okay, so let's write that down, 23747.94, 23747.94. Oh, yep, it matches, we don't have to write it down. So it makes sense if a tractor brand new before it even leaves the lot is $45,000, kind of like a car, right? As soon as you drive it off the lot, it already loses value because now it's not brand new. Now somebody's already owned it and left the lot with it. So it depreciates, and after 5 years, if you were to buy that tractor, it's only worth less than $24,000, right? So over $20,000 less. Okay. Let's do some exercises. Ooh, lots of reading. Lots and lots of reading here. Great. All right, well, this file is up. If you're not able to see everything that I'm reading on the video, the file is up right below the video, so you can always pull that up and read it yourself and just check your work here. All right, population. The population of Bulgaria has been decreasing. I'm going to highlight all this. Decreasing, so I know it's exponential decay, at a rate of 0.89%. So when I change that to a decimal, I divide this by 100. So that's going to move my decimal 2 places over, 0.0089. That's R. If the population of Bulgaria was about 7,450,349 in the year 2005, this is our initial amount, predict its population in the year 2015. So that's 10 years later. So T is going to equal 10. So here's all our information. We know it's exponential decay, so we're going down. So I'm going to use Y equals my initial amount, 7,450, 349 times 1 minus my rate, 0.0089, 0.0089, raised to the T power, and T is 10 because it's 10 years. Right, so now I've got this formula. Now I'm going to simplify it. The only thing I can simplify is changing what's inside parentheses. So 1 minus 0.0089, 0.9911. I'm going to rewrite this. Y equals 7,450, 349 times 0.9911 to the 10th power. And then for the rest of it, to show your work, all you got to do is just solve in your calculator. So 0.9911 raised to the 10th power, raised to the 10th power, gives us this. And then we multiply that by 7,450,349. Times 7,450,349. Sorry for the glare on my calculator. All right, so we get 6,813,203. 6,813,203. 6,813,203. And to know what to round your answer to, put it in context. If we're talking about population, you're not going to have 0.7 of a person, right? So I would probably round that up to 4. 6,813,204 if you kept it at 203, because you could argue, well, it's not an entire whole person, so we can't really round up. So it's either this many whole people, you can't really have an extra 0.7 of a person, right? I don't know. I wouldn't be that specific or that picky. If you put a 4 here or a 3 here, I would take either one. But since we're talking about population and bodies, I wouldn't leave a decimal. Okay. And then number 2, depreciation. It tells us right there from the get-go. I'm going to highlight stuff that I think is important information. Mr. Gossel is a machinist. Machinist. Mr. Gossel is a machinist. He bought some new machinery for about $125,000. That's our initial amount. He wants to calculate the value of the machinery over the next 10 years for tax purposes. So there's T, 10 years. If the machinery depreciates at a rate of 15% per year, so there's our rate, what's the value of the machinery to the nearest $100 at the end of 10 years? Okay, so we've got everything we need for depreciation. So we have our amount we're looking for equals our starting amount, which is $125,000 times 1 minus our rate of change, which is 15% per year or 0.15, raised to the t power, and t is 10. Okay, so now we can simplify that and then put it in our calculator. Y equals 125, 1, 2, 3. 1 minus 0.15 is 0.85 to the 10th. Okay, and then we use our calculator to simplify. 0.85 to the 10th is that much times 125 equals 24609.30 equals 24609.30, and it's said to round to the nearest hundred. So that would be 24,600, which we would put over here in our answer. 24,600 is rounding to the nearest $100 at the end of 10 years. All right, number 3. Move this over so we can read it. Archaeology. The half-life of a radioactive element is defined as the time it takes for 1/2 a quantity of the element to decay. Radioactive carbon-14 is found in all living organisms and has a half-life of 5,730 years. Consider a living organism with an original concentration of carbon-14 of 100 grams. If the organism lived that many years ago, what's the concentration of carbon-14 today? So we're going to start off with our time, T. Concentration of 100 grams. That's the concentration starting off, the original amount. And I think that's all we have. Okay. So we'll write our equation. The amount we're looking for equals the starting amount, which is 100, times 1 minus the rate of change. Oh, what does it say? Half quantity of the element. So it's a half-life considered. Half-life would be 0.15, I guess. Or not 0.5. If the organism lived 537, what's the concentration today? 5730. That would be my guess to set it up, okay? Y equals 100 times 0.5, 5730. Let's see if this makes sense. I'm kind of guessing on this one. 0.5 raised to the 5730 equals 0.5 raised to the 5730 equals just nothing because it's so small. All right, well, never mind. I'm making this too hard. Duh. The half-life. It tells us right here at the top. The half-life of a radioactive element is defined as the time it takes for half the quantity of the element to decay or to go away, right? Half of it, okay? So the question was, if an organism lives this many years ago, what's the concentration of carbon today? This is its half-life, the half-life of 5730 years. So if it started out at 100 grams and its half-life is 5,730 years, and it was made 537 years ago, then today, what's the concentration, right? It's half of 100, so 50 grams. It literally tells us in this many years, half of it's going to go away. Half of it will decay. That's what the half-life is. So if it starts out here and it goes this many years, how much will it be? What will the concentration be? Half of this. Okay, and then again, if the organism lived 11,460 years ago, determine the concentration. So it's going to get cut in half, and then that is going to become the new starting amount. It's going to get cut in half again. This amount is just double 5730. If you multiply 5730 times 2, you get this amount, right? So we started out at 100, then 5,730 years later, we got half of it, 50. And then another 5,730 years after that, you're going to get half of that, right? So it's going to become 25 grams. That was an interesting problem. Don't overcomplicate it. I was trying to use the formula and you did not need to. Number 4, back to regular old decay. A new car costs $32,000. It's expected to depreciate, so we know it's a depreciation problem, 12% each year for 4 years, and then depreciate 8% each year thereafter. Find the value of the car in 6 years. So we're going to actually have 2 different equations here. We're going to use one for the first 4 years and then another one for the next 2 years, because we're looking at 6 total, right? So a new car costs 32. So for the first part, when we're looking at the first 4 years, our starting amount is $32,000. It depreciates 12% a year for 4 years. So 1 minus 0.12 to the 4th, right? So after 4 years, it's going to be a new amount. And then we're looking at 6 years later, so that you've got the first 4 is this amount. And then 2 years later, it will have depreciated this much each year. So let's figure out the first 4 years first. Okay, so this is 32,000 times 0.88 to the 4th. Okay, so if we simplify that with our calculator, 0.88 to the 4th, we get 0.599,69536, and then multiply it by 32,000. Okay, so after the first 4 years, this is our amount, 19190.25. 19190.25. Okay, so after it depreciates the first 4 years, this is the new amount. But we want to know after 6 years. Well, the first 4 years depreciates to this, and then the next, after that, anything after that, it depreciates 8% a year. So now our new starting point is going to be that 19,190.25. 19,190.25 times 1 minus 0.08, and that's just 2 years because it's 6 years total, the first 4 and then 2 more. So now I can simplify this. This much, 19,190.25 times 0.92 to the 2nd power. And so now I'll simplify that in my calculator. So I got 0.92 to the 2nd power. I could have just hit squared. And then this amount times 19190.25. 16242.63. 16242.63. 16242.63. After 6 years, okay? All right, anyone confused on that last little part? We have a car that's depreciating, and over 6 years, what will the new value be 6 years later if it's depreciating? That's all fine and good, but it doesn't depreciate by the same amount over time. The first 4 years of the 6 years, it depreciates at 12%, so it's going a lot faster. And then after 4 years, it kind of slows down. It doesn't depreciate as much. It's only 8%. So the first 4 years, as we depreciate, after those 4 years are up, our new value is this. Then moving forward 2 more years, but only depreciating at an 8% value, 8% rate. 2 years after the first 4, we're left with this amount. Okay, I hope that makes sense. Let me know if you have questions.